So good morning all. Let me just share the screen.
Okay. Tausif sir, are you there? Hello. Okay. How many of you are able to successfully enroll to the course? Please raise your hands. There is a raise hand option is there at bottom. Just click on raise. Okay. Good. Still half of the participants are not able to enroll. Let me know what's the issue. Okay, Aditya, just wait for some time. It may be due to many participants are trying to access at the same time. That's why. Okay, so just keep trying. Even for me, for few minutes back, it was not responding. Just refresh the entire page. Okay. Just once you are done with the registration, raise your hand.
Now, am I audible?
Yes, sir. You're audible.
Okay. So I think most of them have used the event code. So we should start.
Yes, sir. Please go ahead.
Okay, fine.
Okay, still there are half of the participants not yet registered or enrolled to that course. If you are facing any problem, just let us know so that we can rectify it. As I mentioned, that event code is valid for today only. Okay, so as the criteria for this training is you have to submit all the certificates, right? So if you don't have access to the certificate tomorrow, then we cannot help you out. So make sure whatever problems you are facing while accessing the course, try to rectify it now. Rishabh Mukherjee, you can enroll to the course from mobile, but you cannot launch the cloud instance and work on the course from mobile phone. So you have to use laptop or desktop in order to complete the assignment and everything. Just enrollment is possible through mobile phone. Remaining participant, just let us know in the chat box what are the problems you are facing. I'll be here to assist you.
So is my screen visible?
Yes, sir. You can continue now.
Okay. So hello, good morning all. So I think most of you have used the event code. Once entering the event code, you should be on this page. Here there are three buttons. One is for launching the course, another one is for stopping the task, and last one is the final assessment check of the assignment. So you should click on this launch button. Once you click on this launch button, then this window should get opened. So this is the course window. The course is fundamental of deep learning. You can see in the left hand side panel some folders are there. This is data folder, then some sample images are there, and these are some Python notebooks. Mostly this course will be covered in PyTorch. So I will be covering like what is the syntax, how we can write the PyTorch code, etc. But do not worry about the syntax of the PyTorch if you are not very much comfortable in PyTorch. But you should be very much comfortable in understanding the concept behind this. So here we can see several notebooks. This we will try to understand these notebooks, and based on these notebooks, one last assignment is there that you can see over here. That is notebook number 7. So based on this previous notebooks, you need to finish this assignment. Once you complete this assignment, then once again you come back to the previous page and you need to click on this assess task. Okay, if you completed the assignment successfully, then your certificate should get generated over here. At any point of time, if you are having any doubt, then just please feel free to interrupt me. We will have the doubts clear, and then we will move ahead. So we start with the very first notebook. This is the first Jupyter notebook. It is just an introductory notebook, like what is there, what are the various things in the this particular notebook. Some menu bar is there. This is nothing but the menu bar. Then left sidebar is there. So it is just an introduction, like what is there, how we can run a cell, things that you should understand from this notebook, how we can run a cell. So suppose this is a cell. So we just need to click on into this cell and just press Shift Enter for running this cell. Shift Enter is the command for running the or for executing this cell. Once I press Shift Enter, then probably you can see this outcome. This was the first thing. Second thing, how can we clear the GPU memory? At the end of every notebook, you should see this code. This is just a line of code wherein you can see we are just importing interactive Python, and we need to call this do shutdown method. See, whenever you launch or whenever you use the GPU instance on the cloud, then some memory is allocated there, and after that once we finish our work, we need to clear or we need to free that GPU memory so that we can use those free memory in for the subsequent notebooks. Otherwise, if you do not do this, then you might face in execution of the subsequent notebook cell. So see, once I run this cell, and what was the command? Shift Enter. So you should get this kind of message. It means that you successfully cleared the GPU memory. So this were the two things that you should learn from this notebook. So the structure will be like this. We will see first the fundamental of deep learnings, which is required to understand the neural network, to understand the convolutional neural networks, to understand augmentation and transfer learning. And after learning this theoretical concept, we will come back to the notebook once again, and then we will try to execute this cell. So this is the structure. First of all, we will try to understand those presentations, and after that we will come back to this notebook, and then we will try to understand and execute those cells. And when we are on this page, then you can run this cell with me also, so that you can be familiar, like how what output I am getting, what output you are getting, are you getting the expected outcome. Okay, so this is the very first presentation. So basically, here you can understand like why we are at all using the deep learning. So basically, deep learning is a branch or is a subset of machine learning, and machine learning is a subset of AI in turn. So broadly, you can say AI is there, and in AI, ML algorithms are there, and in ML there is a subset known as deep learning. Okay, so basically, this is the total structure of the course. First, an introduction of deep learning. Then, so second, we will see how we can train a neural network. Then in part 3, we will see how we can train a convolutional neural network. Then in part 4, we will see data augmentation and deploying the model on the cloud. What is the actual model deployment? Then use some pre-trained models, and then finally we will see some advanced structures such as sequence models, basically recurrent neural network, LSTM, GRU. Those are covered in this advanced architectures. Now, see, first of all, we will see what is the difference between the traditional programming and the necessity of machine learning in this. So, in like how we, if we can formulate the rules precisely, then traditional programming comes into picture. We are having straightforward algorithms, and one when we are not having straightforward rules, like some ambiguity is there in the data or in the rules, then only we should go for AI, ML, and deep learning. This is the major difference between the traditional programming and non-traditional programming, means ML and deep learning side. Now, suppose if we take an example of building the classifier. So, classifier is a algorithm or is a model which classifies uh, uh, something like it is just a classification model. When we take an example, suppose we are interested in predicting whether there will be a rain today or not. Okay, so this is a classification. So basically, two outcomes are there. Uh, the outcome may be yes, outcome may be no. Okay, only two categories are there. So this is a classification is handwritten digit recognition. So some handwritten digit is given to us, and we are interested in recognizing which handwritten digit is this, whether it is handwritten digit 0, handwritten digit 1, handwritten digit 2. The previous example that we have seen, that was an example of binary classification. The current example that we are looking, that is the multi-class classification. So basically, these are the steps while building a classifier. First of all, show the model with examples, several examples, like this is the input and this is the output. We need to show these examples to the model, and model will take what is the relationship between the input and output. So based on the relationship between the input and output, it tried to predict the outcome for the unseen data after the convergence of the model. Like every model is associated with some parameters. Okay, so model is initialized with some random parameters. When we show the model, okay, these are the our sample data. This is the image and this is the label. Based on this, models are get updated. This process is called as model learning. Like the parameters of the model are getting updated. It is known as model learning. And once the model is trained, like the model has learned the shown data, that is nothing but our training data. Based on this, the model is deployed, and then it is ready for the prediction on the unseen data. That is nothing but the testing of the model. So these are the steps for building a classifier. Yeah, this is what we have seen just before. If rules are clear, then we should go for classic programming, and if rules are complex, difficult to discern, then we should use deep learning. Deep learning means we should understand what is the actual meaning of deep in the word deep learning. Basically, when we can think in this direction, the number of layers in a neural network. So, if number of layers in a neural network is large, then we can consider that model as a deep model or deep learning. Basically, the parameters are there of a neural network. The weight matrix and the bias are nothing but the parameters. Okay, and if you just imagine a neural network wherein 100 to 200 layers are there. When 100 to 200 layers are there in a neural network, then imagine that billions of parameters would be associated with this neural network. And model training means ultimately we need to figure it out, the exact or optimal value of each of these parameters, such that the underlying cost function or the loss function should be minimum. So this is what the overall picture about it. Basically, deep learning is used in two broad categories. One is computer vision, another one is natural. There are various things you can understand, like object detection. one image is given to us and we are interested in predicting which object is this. Then was some example of self-driving cars or driverless cars are there. Then robotics, manufacturing, then object segmentation. These are the very interesting examples when we are looking computer vision domain. If we are looking at natural language processing, then we are having some real-time translation like voice recognition, virtual assistants, like you can observe Siri in Apple phones. Uh, move then these are the example like content creation, targeted advertisement, then shopping recommendation. Uh,
Uh, Tausif
when
sir,
we
your
are
screen is not visible. Yes, it is visible now.
so if you look at reinforcement learning, wherein some agent is there, and based on the outcome, there's some reward is generated. So this type of learning comes under the category of reinforcement learning. Like if we are interested in building some game application or some chatbot, so this kind of applications comes under the case of reinforcement learning. Some positive reward, negative type of rewards are generated. Like if it is good, if the virtual assistant or if the agent is doing good, then some positive remark or positive reward is provided to them. If he is not doing something good, then some negative reward in terms of penalty is learning comes under the category of reinforcement learning. One classic example or very interesting example is stock trading robots. So this robot just predict like what should be the value of this stock, whether it will go up or whether it will go down after some time. Now suppose just imagine that if it is predicting correct, then we will generate some reward and that reward is sent back. Means the agent is performing good. But if it is predicting that the stock should go up, but adversely if it is going down, so this is nothing but a generation of negative reward. Like some penalty should be associated with that agent. So this type of learning is there that comes under the category of reinforcement learning. Yeah, overview of the course that I have already given. So first of all, we should see some hello world program of deep learning. We will train a more complicated model. Then we will see some new architecture in terms of convolutional neural networks. After that, we will see how we can use the pre-trained CNN model, and then we will use finally the transfer learning. Okay. Now this presentation is closely associated with the very first notebook. Here we will see what we are doing and exactly same thing that we will implement in the notebook. Okay. So first of all, we will load the data. This first notebook is related to the building of that deep neural network for the classification of handwritten digits. So firstly, we will load the data, visualize the data. First of all, this is the most important thing, like how we can visualize the data, like what are the various characteristics of the data, what is the dimension of data, Is there any pre-processing that is required for the data? That is nothing but our step number 2, editing our data. Some shape change is required for processing the data by the model. Is there any normalization that is required? Should we convert the model in some categorical form? We provide which type of optimizer that should be used. Then for gradient descent that we are using, is there any optimizer that we are using? So these are the things that we will define after the compilation, and after compilation we will train the model on our data, and lastly once the model is
Sir,
trained on
again,
the
your
data.
screen is not visible.
Sir, now it is visible,
Yes, sir.
but I think after some time it goes like I need to reshare it once again. I don't
I
know.
think so. I'll let you know if it is not visible.
Okay, fine. Then once the model is trained, then we need to figure it out on the unseen data. Basically, the entire data set is divided into 2 or 3 parts. The first set is a very compulsory set known as training set. Then next set is validation set, and the last set is testing set. So on training set, it is very much clear that we are training the model on this training set. On validation set, we will just find out like how the model is performing on validation set. Uh, Based on of the validation set performance, we will try to tweak some hyperparameters of the model, and we will try to minimize the loss of the validation set so that our model should perform well on the training set as well as on the validation set. So there is a difference between training set and validation set. Training set update the model performance in terms of model parameters, and validation set update the hyperparameters. Validation set has nothing to do with the model parameter. The test set is there once the model is deployed, then finally the testing set is there, and on test set the model is evaluated last. Now this type of data is given to us. It's a handwritten digit. The dimension of this handwritten digit is 28 by 28. So 28 rows are there, 28 columns are there. This data is in the form of numbers. So it's a matrix. Two-dimensional array is there, that, and this data is associated with some label. Like suppose here we can observe this image is of handwritten digit 5. Okay, so this is the input X, and one label is there, that is Y. Okay, generally input data is associated with the variable X, and generally label is represented with the help of variable Y. So it is our data. You can see this is a black and white image. That if it would be a colored input, then 3 channels like RGB, 3 channels would be there. In that case, the size of data or the shape of the data would be 28 by 28 by 3. But here the data is 28 by 28 by 1. 28 is width, 28 is height, and 1 is the channel. So basically this type of model that we are interested in creating. So 128 by 28 input is given to us. So it means total how many values? 784 values are there. 28 multiplied by 28. If we convert all these matrix numbers in the form of a vector, then it will be total 784 values. So this is my input for the neural network. After that, I will be having one another layer of neuron in which I will just decide like how many neurons would be there in this layer. So it is totally depend on our choice. So it is nothing but hyperparameter of the network. So basically 512 neurons that we are taking over here. Then we are a neuron wherein once again 512 neurons are there. So this is my first layer, this is my second layer, and lastly my output layer is there. So if we consider the case of handwritten digits, total how many classes are there? It's a case of multi-class classification. So total 10 categories are there. So here you can see total 10 neurons are there in the output. And what this 10 neuron will predict? The first neuron will predict that what is the probability that this image belongs to handwritten digit. Second neuron will predict what is the probability that this input digit is of handwritten digit 1, handwritten digit 2, handwritten digit 3 up to handwritten digit 9. And yeah, this is the neural network that we will build. Basically, it's a case of a very simple model. If we take an example of line fitting or any curve fitting kind of example, so this is my input and this is my label. Initially, I can start from any random points. We don't know the value of this M and B. See, you can closely resemble this problem with the help of a neural network. So here, see, X is the input, Y is the output. So X is the input and Y is the label. And this M and B are nothing but the slope and the intercept of the line respectively. But if you look at the this particular scenario in terms of a neural network, then this M and B are nothing but the parameters of the model. Our ultimate aim is that we are given with this X and Y, Y is 3, when X is 2, Y is 5. We don't know what is the relationship between this, like how Y is determined from this X. Okay, our ultimate aim is that we need to figure out the values of M and B such that when some X is provided, then we should be optimally finding the value of Y. This is the ultimate aim. So initially we don't know the value of M and B. We take any random value of M and B, and after that, with the help of this loss function, any loss function that you are using, it depends on the problem or the applications. So our aim is that we are interested in minimizing the loss function. And how we will do this in neural network? We will do this in a neural network in terms of with the help of gradient descent and backpropagation algorithm. So do not go in the mathematical details of this, but what ultimately it does, it will just partially differentiate the parameters with respect partially differentiate this loss function with respect to the free parameters, and based on that it just parameters M and B slightly such that this MSE or mean squared error or root mean squared error, the value of this loss function or cost function should be, this is the ultimate aim. Basically, see, this is suppose our target where the loss function or cost function is minimum. So we need to change the value of M and B such that we will take some small step and we will reach to this particular. Ultimately, the back propagation or the gradient descent work similarly. There are various optimizers. The algorithm that we have studied, such as gradient descent or backpropagation. So, for faster convergence of the model, what do we mean by that? Faster convergence. See here, this is step one, then step two, step three, step four. So these many steps are there. Okay. So suppose imagine that in suppose 7 steps we are reaching global minima where the loss or cost function is minimum. With the help of these optimizers, ADAM optimizer, ADA grad, RMS prop, ADA delta, Nestro, stochastic gradient descent, we are just interested in minimizing the steps for reaching towards local minima. This is the ultimate aim of these optimizers. Basically, we will be using Adams optimizer in our notebook, which is just a combination of momentum and RMS prop. Do not go in the details of this, like how Adams algorithms are interested. Then you can go to the read, like what do we mean by RMS prop optimizer and what do we mean by momentum. Because Adams is nothing but a combination of both of these techniques. Yeah, this is our neural network. Some inputs are provided to this. Every connection is associated with these weights. Okay, every weight, and this is our prediction. This prediction is compared with the label. Difference between the prediction and label, we will try to change or update the value of these parameters W1 to W6, and we want that the label or the prediction should be as close to the label. This is our ultimate aim. Now there are various kind of activation functions that we should use. One activation function is linear, like this wx plus b, but generally the applications that are there in nature are kind of non-linear. So there are various activation functions non-linear. Examples of this non-linear activation functions are sigmoid, ReLU, 10H. So we can use any non-linear activation function, but preferably in the notebook we are using this ReLU, rectified linear unit. So the formula is this: if it is less, output 0, and if it is greater than 0, that exact value that are getting over here. Next is a very interesting problem and very important problem: overfitting. But we will not cover overfitting now. We will switch to the. We will try to run every cell of that notebook, and once again we will come back to the overfitting. Okay, next try to learn this cell. Basically, here what we are interested in doing, here we will try to implement this image classification with MNIST dataset. So all of you on this page, you can just raise the hand. Basically, it's a hello world kind of problem. The objective of this notebook is we will try to build a very simple deep neural network for handwritten digit classification. See which type of handwritten digits are this. This is our input. It's a handwritten digit 0, it's a handwritten digit 1, handwritten digit 2, it is also handwritten digit. Basically, we are interested in building a classifier which can classify which handwritten digit is this. And what we are implementing a very simple, plain, deep neural network. But what do we mean by that? Uh, it's means multiple layers would be there, and neurons of the previous layer. This is nothing but fully connected fashion of connection in a new. So basically, we are using this PyTorch. Then we create the model and we will see the performance. Basically, are the some libraries we are using Torch. Then we are using this neural network. Then some data sets which are already standardized data sets are there. Then data optimizers. Then these are the visualization tools. Torch vision, transform is a technique which transform the data as per our need. Like suppose we are interested in transforming the data from three-dimensional to two-dimensional, then we can use this kind of transforms. Then some matplotlib library is there which is used for plotting the image. So these are the libraries. Just run this cell and remember what is the command for running a cell? Shift enter. So we need not implement anything. We just need to understand the notebook and we need to execute the notebook. We need not implement anything. We just need to understand what is there in the notebook and we will just execute the notebook and just analyze the outcome. See, first of all, we need to identify whether the CUDA is available or not. So first of all, there is a command like CUDA.device. First of all, we will check if torch.CUDA is available. So it a boolean value. If it is true, that means that CUDA is available. So we will set device to CUDA. If it is returning false, then we will return CPU. Okay, and we will just print whether the CUDA is available or not. Okay, so see, if it is returning true, it means that CUDA is available for our use. GPU is available. Okay, so this is the problem, and the solution is deep learning. If you look at the data set, so total 70,000 images are there. All these images are grayscale images and handwritten digit line. So total 10 categories are there. So these are the image. Now, as we have earlier discussed, that this should be categorized to training and validation data. So first of all, training set and validation set are there. X is our input, Y is our label. Okay, so based on the pairing of X and Y and training and testing categorization, we should be having these four variables. X train means training set images, and Y is used for label. And suppose when we are writing Y, it means that labels of the training set. Then X validation means validation set images, and Y validation means labels of the validation set. Basically, total 70,000 images are there. See, these 70,000 images, yeah, this 70,000 images are classified into two categories: 60,000 training images and 10,000 testing images. Okay, this data is already available. We need to just load the data from this torch vision dataset. We are defining here training set, we are defining here validation set. So torch vision dataset.mnist data is available. If it is belonging to train set, then train is equal to true. This attribute should be true for training and this attribute should be false for validation. Okay, and both should be downloaded, and this is there in the root folder. Okay, it is available in torch vision. We just need to now just look at that. If we run train set, what should be the output? See, number of data points. So total how many images? 60,000 are there. Each data point is having image as well as its label. So image and label is nothing but one data point. Then second image and its label is nothing but second data point. It's a training. Validation, just run this cell. So total 10,000 images are there. Then it's a testing set or validation set. Now we will try to understand the characteristics of the data. What we will do, we will see the first sample. Get the first sample from training set. Train set of 0 means the very first sample. In that first sample, image is also there, label is also there. So x of 0 is nothing but my image and y of 0 is nothing but my label. Just run this cell. Now I am printing x of 0. See what is the output. This is image, and y of 0 is a label. Which what is the data type of this? Suppose I am interested in printing the data type of this, then I need to type print. So here, see, you can see the type is, it's the image. Okay, y of 0 is a label. Which type of label is this? 5. See, this was handwritten digit 5 and it is the label 5. And what is the data type of this? Data type is integer. Fine. Now we will try to understand the tensor. Tensor is nothing but a matrix. It can be a one-dimensional matrix or two-dimensional matrix, three-dimensional matrix, or any multi-dimensional matrix. It is nothing but, everything is nothing but the tensor. We are defining everything in terms of tensor. So here what we are doing, we are just converting that matrix or that image in the form of a numbers. How we can do this? We are having some transform dot compose. Here we convert this into two tensor. With the help of this two tensor function, we will try to convert. And what we are converting? We are converting this x of 0. What was there in x of 0? This is my x of 0 image. Size is 28 by 28. This should be converted to a matrix, having this compose and two tensor. We will just try to convert it, and which variable we will be using? X of 0 tensor, and then we are printing the data type of this. See, x of when we are applying this compose, previously the range is 0 to 255, but when we apply this two tensor, then it convert it into numbers, as well as it apply the normalization. So how normalization is applied internally? Every value of this matrix of size 28 by 28, every value is divided by 255. So the initial range was 0 to 255. Now the new range would be 0 to 1. Okay. Now just run this. See the type. Here we can see the type is floating point 32. Okay. Min 0 and maximum is 1.0. This is how you can convert the images into tensor. Okay, so far we have just converted only single uh, cell or only single image into tensor. Ultimately we need to do this for all the data set, that is the training as well as validation set. Now see the size of this tensor. Size of this tensor is 12828. See, this one indicate, this 28 indicate the number of rows, 28 indicate number of columns. Okay, in PyTorch, number of channels is the very first thing, then height, and then width. Suppose if I print x of 0, so the matrix is get printed out. See, this is the matrix. Here you can observe that this is the first matrix, this is the first row of the matrix, then this is the second row of the matrix. And how many values are there in each row? 28 rows. And how many such rows are there? 28 values are there. The 28 rows are there. Everything should be moved to the device or to the GPU. This should be moved to the GPU. Then we will check whether we have moved it successfully or not. So this should print CUDA if the movement is successful. Otherwise, it should return some error. Now we had converted that image to the tensor. That tensor to the image with the help of 2PIL image function. Once again, we are passing this tensor. Okay, that tensor is once again showing this image. See, it's handwritten digit 5. 28 rows are there, 28 columns are there. Now next step is preparation of the data for training. So we need to once again apply the transform function, and we will use this compose and to tensor. First of all, we will perform this, and we will create this trans over here. This trans will be applicable for training set as well as validation set. So train set is also transformed, validation set is also transformed with the object created over here. Okay, so entire training set is converted to a matrix, and entire validation set is also converted into matrix. What how training set is converted? In training set we are having images and labels. Okay, the images are converted into matrix, two-dimensional matrix, and the labels are converted into categorical form. What is the meaning of this? That suppose the label is 5, another image is there, suppose the label is 6. Okay, we do not want to represent the label like this. So what ultimately we do, we convert this into categorical form. So total 10 categories are there. We just convert this label 5 into a vector. Okay, in that vector, the fifth entry would be 1, and rest all will be zero. Rest other entries are 0 when it is handwritten digit 5. Suppose if it is handwritten digit 0, then the very first entry would be 1. If it is handwritten digit 9, then the last entry would be 1, and rest all will be 0. So conclusively, in that vector, size of that vector would be 10. Only zeros and 1 would be there. Only one time 1 will be there, and remaining all entries would be 0. So this is nothing but the better representation, and it is used for converting or for efficiently calculating the loss function. Next, come to the data loader. Data loader, as the name suggests, it load the data. Okay, it just collect the data from training set and it load the data. It ultimately depends how you are loading the data. What should be the batch size? Suppose, see, when we are when we are considering this batch size is 32. So just imagine a case where we are having 60,000 samples are there. Batch size is 32. So what the data loader will do? It will take a random 32 samples from training set, and then it will pass to the model. Then it will take second set of 32, then pass it to the model, then take the third set of 32 sample, pass it to the model. This is the role of batch size. Why it is important? Because it effectively manage the memory, because we cannot load the entire 60,000 samples in the GPU memory. We are not having that much enough GPU memory over here. Generally, the batch size is 32 or in multiple of 32, such as 64, 128, 256, like this. Okay. So see here, we are defining this data loader for training set as well as for validation set. Here we have defined batch size is equal to 32. Then see, this is my data loader. Here what? Shuffle is equal to true means it will randomly select a set of 30. It will randomly select a set of 32 samples.
Sir, screen is not visible. It's
So
visible now, sir.
So shuffle is equal to true is applicable and is beneficial for training set only. And what it does, it take randomly selected sample from the training set, and 32 samples would be provided to the model. Okay. And now These are the two main variables that we train loader as well as validation loader. Okay, just run this cell, and then next step is creating the model. Now flatten. Whatever we are having, we need to convert it into a vector first, because everything should be provided to the deep neural network in terms of vector for this particular model. So if we are having a cell or 32 32 or 28
Uh,
by 28,
just 1 minute, sir. Uh,
yes.
there are few students. I think they are saying no audio. Others, could you please confirm if it is audible or not? Okay, fine, fine. So I think Deepak, the problem is at your end. Just check it. Okay, sir. Please continue.
Okay, so flatten layer is the very first layer. Whatever we are having in the form of matrix, that we will convert it into a vector. This is the first thing that we will do. Then after that, we are having another layer of neuron. That is the first hidden layer, in which 512 neurons are there. Then second hidden layer, wherein once again 512 neurons. And then last layer, in which 10 neurons are there. This is the model that we are interested in building. First of all, we are defining this set of layers. Initially nothing is there. Okay, then flattening the image. See here, this is just an example like how flattening works actually. So here what we are providing, here we are providing a 2D matrix. Okay, see, and then once we apply the flatten to this test matrix, we will see the output. Okay, here we will see it is not getting converted into a vector. Even after applying flatten layer, it is not getting converted into a single vector. The reason is that because it accept the data in the form of batches. So here we can consider that it's only a not two-dimensional matrix. It is considering this as a multiple 1D array. Okay, so if it is the first 1D array, then it is the second 1D array. Ultimately, it vectorize this, and it will not converting into a vector just because we are not applying this test matrix in terms of batches. How can we convert this in terms of batches? See here, we need to provide one extra dimension over here. So with the help of this none, we are providing one extra dimension. Okay, see here one extra bracket that you can observe over here. Now the entire data is converted into a batch. But how many samples are there in the batch? Only one sample are there in the batch. Now we can apply flatten. So this time it will get converted into matrix into vector. Okay. So entire batch should be provided as input. That's why it will, then only it will work. Now see, in layers we are adding the very first layer, that is neural network dot flatten. Okay. Then input layer. What is our input size? 1 cross 28 cross 28. This is my input size. Just run this cell. See, I am defining the layers. This is my flatten first layer. After applying the first layer, that is converting the matrix into vector, then we are having input size. What is our input size? That we have just defined now. 28 by 28 multiplied by 28, that is nothing but 784. So 784 values are there in input, and 512 neurons are there in the output. Just a minute. See this one. This one. 784 values are there in input, and 512 neurons are there in the output. Every neuron in that hidden layer is activated with the help of nonlinear activation function, and that is nothing but this neural network dot rectified linear unit. Okay, just run this cell. Here ultimately we have not created any model, we are just adding the layers. Okay, now we are adding one more layer. This we had already added. Now this time we are adding one more layer, in which 512 neurons, this 512 will act as a input for this layer, and once again this 5 into neurons. After that, we are adding one output layer. Number of classes that we should define. Number of classes is equal to 10. So first of all, this is my first layer, then this is my second layer, and this is my last layer, in which total 10 neurons are there in finally. Once again, I am printing the layer. So far, I have not created the model. Okay. Now I need to create a sequential model. Sequential model means layer after layer is are there. So I will just call this nn dot sequential. It will create a model, and I will just pass this star layers over here, and then it will return to this model, and then the model is created. Now see, this is my model. It's a sequential model. The very first layer is the flatten. This activation function for this layer. Then next is this hidden layer. Activation function is ReLU. Then this is the last layer. Everything should be moved to the GPU. See, model dot to device. What ultimately we are shifting to device? We are shifting the parameters to the device. Here we can see, just try to run this cell and see the output. Here it will print which type of device is there and what is the GPU index that we are having to work with. Okay. Then we are having torch.compile. We just need to compile the model for faster performance. You can find the details of this, what ultimately it does compile in the backend. Okay, but ultimately you can try to understand that it is just for the faster performance. We need to compile the model. So the things are like this. First, you need to create the model. Then you need to compile the model. After that, you need to define which type of loss function that are there and what are the optimizations. So here we are using cross entropy loss. There are various loss functions available. It completely depends on the application that we are having. Here we are having application for handwritten digit recognition. So for this, another loss function that we are using is cross entropy loss. Any optimizer that we are using? Yes, Adams optimizer that we are employing over here. Now finally we need to calculate how the model is performing. Before doing that, we need to define what is the length of the train loader and what is the length of validation loader. Okay, so we need to just print this. Okay, but suppose if we are interested in finding what is the value of train n, so we can also change this cell and just append this train n. Okay, here we can also append this validation n. Okay, now just run this. So validation n is nothing but 10,000. Similarly, train n would be 60,000. So this is nothing but the actual length of the training set, and these two variables that we are using, train n and validation n. Now everything is happening in terms of batch. Okay, batch of size 32. So what we are doing, this is a function that we are defining for calculating the batch accuracy, and three parameters that we are passing into it. One is that output, another one is the y, which is nothing but our prediction, and then n. Okay, what we are doing over here, first of all, we are getting the maximum value of the each and every sample for the batch. Just imagine that 32 outputs are generated. The length of one output is 10 because 10 neurons are there. So what we will do in each of these outputs, okay? Now we will compare these outputs with the actual one, okay? And we'll see how many of them are correct. So what it is returning? It is returning the total correct prediction divided by this n. This is the batch accuracy. Then we need to define two functions. One is train function and another one is validation function. See, this needs to be understood only in the first notebook. In rest all of these notebook, the same thing is happening in the subsequent notebooks. That's why I am explaining this in detail. This is the training function. Loss and accuracy are 0. Model dot training, it just initiate and just inform that okay, the model training is getting started over here. Now xy, and from where we are taking xy, we are taking xy from the train loader. Okay, 32 samples are provided in first iteration. 32, because 32 is the batch size. X y is equal to x dot 2 device and y dot 2 device. First of all, this batch should be moved to the GPU. Now in backpropagation, we are having 4 steps. First, calculate the output. So this is the output. Second, defining the loss function. So optimizer dot zero gradient. This is nothing but calculate defining that okay, this optimizer that we are using and initially it is not having any gradient. Then we need to define the loss function. So it is having loss function, and the loss function is nothing but the difference between the predicted output and the actual label. This output is nothing but predicted output and this y is nothing but the actual label. Then backward pass. So gradient is back propagated from the loss function to the initial layers. This is the third step. And last step is nothing but the parameter updation, optimizer dot steps. So total 4 steps are there in back propagation. One is forward pass, in which we compute the output of each and every neuron. Second, computing the loss function. Third, computing the gradient of the loss function, like partial differentiation of the loss function with respect to every free parameter, and then last one, updating the parameters. After doing these 4 things, we need to find loss is equal to loss plus batch loss of this particular batch, running every time. Like first batch is coming, and then it is loss is accumulating in this. Then second batch is coming, then loss of second batch is accumulating in this. Similarly, loss and accuracy are getting accumulated over here. And see, in accuracy, we are passing this. We are calling the function get batch accuracy. Accuracy is equal to accuracy plus get batch accuracy. Now see, 3 parameters we are passing over here. Output is nothing but our output or the predicted output. Y is nothing but actual label, and train n is nothing but the total number of samples. But see, why we are passing this total number of samples over here? Because we are working on the batch of size 32. So should we pass here 32 or should we pass here 60,000? So this is the question. Just think on this. And then finally this loss and accuracy are getting printed out. Just run this cell. This was my training function. Next one is my validation. Similarity between training and validation. Loss and accuracy are once again defined as 0. Model dot evaluate will just initiate the model evaluation. Torch dot no gradient, it means that in validation gradients are not getting updated. Ultimately the model parameters are not getting updated over here for xy. Now this, from where xy should be coming? Xy is coming from the validation loader in the batch size of 32. They should be moved to the GPU. This is the very first step. Calculate the output. This is the only thing that we need to do. Calculate the output. No need to calculate the gradient. No need to update the parameters because it's a validation. Here we are not updating the parameters. Now this is my validation loss accumulation and validation accuracy accumulation. Here also we are calling this function. We are passing this output y and validation n. Once again the same question. Here validation n is 10,000, but here we are working on batch of size 32. Should we provide here, should we pass 32 or should we provide 10,000 over here? Then this is my validation function. So we define training function, we define validation function. Next, the final execution or final training for epoch in 5 times we are running the model or the very first thing is print which epoch is this. Epoch is nothing but consideration of all the samples. Train means train the call the train function. Validate means call the validate function. Just see, this is the epoch 0. You will see the outcome over here. It will take some time to run. See, this is my training loss and training accuracy. Then this is my validation loss and validation accuracy. Then next epoch is started. This is training and validation for epoch 1. Then this is training and validation for epoch 2. You can subsequently observe that loss is getting increased across subsequent epochs. Okay. And then this last cell that we are passing, model is evaluated on this x of 0.gpu, and we will call this prediction, like what is the outcome of this. See, when we run this cell, see the output. The previous this is okay, fine. This is epoch 4, means the last iteration. Okay, because we are running it for 5 epochs, 0 to 4. And this is my outcome. See total how many values are there. These are the 10 values. The final last layer in the neural network was the linear layer. We are not applying any activation function on the last layer. So this is the outcome of first neuron, this is the outcome of second neuron, like this. And we need to take the maximum entry over here. See which entry is maximum over here, this 17.44. Okay, so this is handwritten digit 0 1 2 3 4 5. So this is handwritten digit 5. We can take the maximum of this. See here, we can apply prediction.org max across this first dimension, and keep dimension is equal to true. So here it will return the index. Okay, and what is the y of 0 means the actual label. See, actual label is also 5. So this 5 is my prediction. Okay, and this 5 is my label. And lastly, clearing the GPU memory. Clear the GPU memory. Okay, we successfully cleared the GPU memory. Yes, any doubt, any query? You can also run this. You are getting the same or similar kind of outputs. So we will take a break of 5 to 10 minutes, and we will once again start at 11:25. So I hope my screen is visible. We have seen the very first notebook.
Yes, sir.
Now we will move to the next notebook. In next notebook, we will do exactly same thing, but the only difference is that previously we did it for MNIST dataset. This time we will be doing it for American Sign Language dataset. Exactly same network that we are interested in building. First initial input layers is there, then next first hidden layer wherein 512 neurons are there, then next hidden layer in which once again 512 neurons, and then last layer in which total number of neurons would be is equal to the number of categories in this particular classification. Once again, we are importing this libraries. Then this is the American Sign Language dataset. Okay, see, this type of images are there. Once again, it's a grayscale image. Black and white image are there. A number of channels in the input is equal to 1. This is the label. Then this is the image. This is the label. So from this A to Z, we can work out on all the categories except J and Z, because this J and Z, this requires some movement. Okay, if we exclude these two categories J and Z, then we are left with 24 such categories. So once again, we are interested in building a classifier with the help of deep neural network, where in total 24 output categories are there. This dataset is available on Kaggle. Okay, and we will see which type of dataset is this. Once again, we need to define the same four variables: x train, y train, x validation, and y validation. See where this dataset is available. This dataset is available in this data folder. In data folder, ASL data is there, and then sign MNIST train. Do not get confused with the name, as the name MNIST is there, but it's American Sign Language dataset. We can also see the data in the left hand side panel. Just double click on this data. Here ASL data is there. This is ASL data, and here two Excel sheets are there. Two CSV files are there basically. So we need to import this data, and we are using this time panda frames, okay, for this. So train df is nothing but training data, and validation df is nothing but validation data. So we do not know like which type of data is this, to what is the characteristics of the data, what is the shape of the data. So for that, what we can do, we can just print some of the rows, or some of the initial values of the train df. So for that, we are having one function dot head. So we will just print train df dot head. So here we can observe this type of data is available. First label is there, and then finally all the values are there. So this total, how many such values are there? This is 785 columns. So if we exclude the first column, this is this label. So that is nothing but 784 values are there. 784 is nothing but all these values corresponding to a matrix of size 28 by 28. Okay. Now see what we need to do. We need to extract everything in those four variables: x train, y train, x validation, and y validation. Training set images, training set labels, validation set images, validation set labels. Okay, now how can we do this? So first of all, we need to pop, or we need to remove this label column. See, this is my label column. We will pop from here. This label of training is nothing but my y train, and the label of validation is nothing but y validation. So we will pop both of these. See, label is popped out from train df, and it is nothing but my y train training set labels. Once again, this label is popped from validation df, and it is nothing but my y validation. After that, I can also print y train. Okay, now we have defined two variables. Which two variables? Y train and y validation. Now I need to define x train and x validation. See, we popped one column, and remaining everything is nothing but x train and x validation. So the remaining values of train df is nothing but my training set images, and the remaining values of validation df is nothing but my validation set images. Fine. Summarizing the data like shape, just look at that. So Shape is this 27,455 by 784. So total, you can observe over here how many samples are there in training set. 27,455 samples are there. Okay. Shape of one sample is 784. What should be the shape of Y train? Shape of Y train is nothing but 780. Sorry, 27,455. See, these many images, these many labels. ये this we are talking about training data. Okay, fine. Now we will see validation shape. This is validation and this is labels. So 7,172 validation images and 7,172 validation labels are there. Fine. Now we can visualize the data with the help of matplotlib library. So here we are printing some 20 images along with its label. So just run this cell. Here you can see some images are there along with the labels. So the labels are printed in terms of the indices. Okay. Here A, B, C, these are not printed. The indices of those labels are printed over here. Like suppose if it is label A, then index is 0. If it is label B, then it is index 1. Okay. Up to last index is 23 because index are starting from 0 and last index is 23, means 0 to 23 means 24 indices are there, and it's a 24 category classification problem. We are not considering those two uh, category J and Z because those require movement. Next one is normalization of the data. We will see which type of data is this. Minimum is 0, maximum is 255. So we do not want to operate upon these large values. That's why we choose normalization. If we divide each and every entry by 255, then the range which was earlier 0 to 255, this range would get converted to 0 to 1. Do it for training set and do it for validation set images, not with label. Okay. Now we can define some custom data set. So basically here we are defining one class. Some my class is there. This is our initialization of the object. When one object is initialized with this class, then these are nothing but some existing parameters that can be assigned like self, xdf and ydf. So we just convert this into tensor and we also send the data to GPU. Okay, this is another function which just extract any particular item. So here we can see, suppose one ID is provided as input, then on this ID, what is my input image and what is my label. So both are extracted. And another function in this series is nothing but length. Like suppose we call this function length, then it is returning length of this particular object. So we can just run this cell. After that, loading train loader and data loader. So here see batch size is 32. First of all, I need to create a custom data set. Here my data set that we call, it is nothing but object. Two parameter we are passing, x train and y train. Training set images as well as training set labels, both are passed to this. See here my data set. Once we create an object, this method is called automatically. Okay. And what we do, self.access is nothing but my training images and self.ys is nothing but my training set labels. Okay. Next thing, I need to create this data loader. So here in data loader, this training data is there, train data, batch size is equal to batch size and shuffle is equal to true. Fine. I will also find out the length of this train loader. So length of train loader dot dataset is stored in this variable train n. Exactly same thing that I will do for validation data. First of all, validation data is customly created. Then this is data loader for validation data, and this is my length of the validation loader. Just run this to cell. If I print this train loader, then see what is get printed out. It's a utility of type data loader. Okay. Then here you can see if train loader is useful or is doing loading the data set, like it load the batches, or batch size is 32. So first of all it load the first batch, then it load the next batch, then it load the next batch. Likewise, this is the task of data loader. So if we run this cell, so it will just fetch the first batch. Fine, this is my first batch. If I run this cell once again, then it will fetch the second batch. Fine, if I run this cell once again, then it will fetch the third batch. So this is the task of data loader, loading the batches. If C batch 0 dot shape, what should be the output of this batch, first batch dot shape? So the first batch, total how many samples are there? 32 samples in every batch. So 32 by 784. Once again, the second batch is of same size, 32. Why not 784? Because see, there is a difference between batch 0 and batch 1. Batch 0 is corresponding to images and batch 1 is corresponding to the labels. That's why here we are getting 32 784 and here we are getting 32 only. And moreover, you can understand that these are not separate batches. These are not separate batches. This is the first item of batch and this is the second item of the batch. See what we are extracting in batch, we are extracting this in a batch. So in a batch, two things are there. One is image, another one is label. So if we call this or if we talk about batch of 0 means we are talking about images. And if we talk about batch of 1 means we are talking about the labels of the same batch. That's why this is 32. Next, building the model. It is exactly same that as we did in the previous one. Input size is 28 by 28, number of classes 24. Sequential model that we should build. See here, you can try like what should be there in the sequential model. Moreover, if you are not very much comfortable at this point of time, you can just click the solution. Just click on this triple dots. You will see the solution. Okay, this is what they expected you to write in this particular region. Okay, but anyway, so first of all flatten, then 512 neurons, then again 512 neurons, and then lastly 24 neurons in the final layer. So this is my sequential model. Last time we created layers, then we passed pointer to the layer, and then we created model. But that is a lengthy process. Internally, the same thing is happening over here also. But you can write here. That is more easiest way to create a model. Now compiling and sending the data of the model to the GPU. Then once again cross entropy loss and Adams optimizer. Training the model. Okay. So train and validation. These two functions are exactly same. No difference is there. Train and validation df. Next. Okay, here see the function below has three fix me's are there. This is one, okay, this is second one, and this is third one. If you remember that what was there in the previous fix me, then you should replace this fix me with those things. Okay, if you are not very much comfortable at this point of time, you can see the solution, or otherwise you can see the previous cells. Okay, see here the batch accuracy is there. This is my batch accuracy. Output dot orgmax. So here this fix me should be replaced by output. Then this is prediction, view as this prediction, then summation of this, and probably those single valued tensor is converted into a number dot item. Okay, then what we should write over here, y is nothing but our label. Okay, and correct divided by fix me. So this n is written over here. Okay, or otherwise you can just click on this triple dots, you will see the solution directly. Just run this cell. So we define train function, we define validation function, we define batch get batch accuracy. Now we need to run this. For this time we are running it for 20 epochs. This is my first epoch. Then we will call this to function train and validate, and we will see the performance. Then epoch 1, we will see the performance. Epoch 2, we will see the performance. Epoch 0 to epoch 19 is there are total 20 epochs. See here, this is the final result. Now here we can see this is my training loss and training accuracy. So here you can see the training accuracy is 97%. It is perfectly fine, not a problem. But here we can see the validation accuracy is around 80% only. Now this is the problem. Okay, but before understanding the problem, let's first clear the GPU memory. Now understand the problem. Once again, we will jump to that previous presentations. Okay, this is the problem: overfitting. Overfitting is nothing but the performance difference between the training set and the validation set. If my if my model is performing very good on training set, we expose training set to the model. Now the model is performing very good on training set. But when we expose the unseen data to the model and model is not able to perform good on the unseen data, then our model is of no use. Now the model is not performing good on the testing data or the on the validation data. So ultimately, there is a performance difference between the training set and the validation set. This problem is known as overfitting problem. It is very well known problem of deep learning or machine learning model. There are various methods for reducing this overfitting problem. And what do we mean by that? Reducing the overfitting problem, we just need to minimize the difference. What we want that model should perform well on the training data as well as it should perform well on the validation data. There are various types of regularization techniques that we can use, like L1 regularization, L2 regularization, dropout regularization. We can use augmentation techniques, like we can introduce the variation in the data set. There are various augmentation techniques that we can introduce in the data so that it can capture the specifics related to the variation in the data and it will perform good on the unseen data. These are the techniques that we can use. See, this is the things. The with the help of this, we can understand overfitting. See, here this was the data. We built a very complex model. Now it is performing very good on the training data. But see, what should be the generalizational capability of the model? It is very low. On the other hand, if you look at this second scenario, so it's a very simple model. Okay, what do we mean by that? Simple model. Only two parameters are associated with this, as it is a line. So slope and intercept, two parameters are associated. But on contrary, just look at this complex shape. Multiple parameters are associated with this model. So first thing, this model is very complex. Second drawback, this model generalizational performance is not good. On the other hand, this model is very simple. The generalizational performance of this model is not that much bad. Okay. So we want simpler model such that the generalizational performance of the model should be good. Now this is plot between the training epochs and the error on the or the loss function. Here we can see the training error is getting reduced. At some point of time, it is getting stabilized. Now it is not getting reduced. Validation error, here we can see when we are training this model again and again. So after some point of time, validation error is getting is not actually reducing, it is getting increasing after some time. The problem is that model is able to capture the specifics of the data, and model is not capturing the generic trend of the data. This is the major problem with the neural network. Okay, and that is nothing but the overfitting. So the performance difference gap between training and validation, this is getting increasing. Okay, and it is nothing but model is getting overfitted. Now, see, we will try to understand the convolutional field neural networks. Basically, in convolutional neural network, what happens? Convolutional filter is there, which is revolving over the input and aggregating the extract the feature maps. Okay. The only difference between the convolutional neural network and the fully connected neural network is that in fully connected neural network, a neuron is connected to all the neurons of the previous layer, but this is not the case with CNN. In CNN, a neuron is connected to only a local region of the previous layer. Okay, that's why less parameters are associated with this, and the same filter is revolving over the input. You can understand like this: suppose one filter is there which is responsible for extracting the vertical edge. Okay, now the filter is revolving over the input and searching for the vertical edge. Another filter is there which is revolving over the which is responsible for detecting the horizontal edge. The filter is revolving over the input and detecting the horizontal edge. This is the philosophy behind convolutional neural network. Now see, this is my original image and this is my kernel. Okay, and how it is worked actually. This kernel is applied on this first 3 cross 3 input, perform element wise multiplication, and then it generates the very first entry. Then it generate the next entry. This filter is shifted one position right. Okay, one position right means on this region. Then it is generating the next entry. Then it is shifted one position right, then generate the next entry. After that, some one position down, then it is generating the second row, then it is generating third row, like this. So this is the CNN working. Stride, by which the filter is revolving over the kernel. See here in this example, kernel is same as filter. So filter is shifted by one position. That's why stride is one. There is a possibility that it should shift by two. It should shift by three. Okay. So here we can see when it is shifted by one, then this is the generated feature map. When it is shifted by two, then this is the feature map. Excuse me. Then it is shifted by three. Then this is the feature map is generated. Shifted by 2 means 3 cross 3 filter is there. Okay, on this region it is there. After that it shifted and then it is generating this. Now sometimes first of all we will try to understand what is padding. Padding is nothing but padding the boundary, padding the zero on the boundaries of the input. Okay, that is nothing but zero padding. Okay, here see, this is my input and on the boundaries we are padding this zero. Sometimes there is a necessity that if the kernel do not fit perfectly on the input, so we are not having a perfect one-to-one multiplication from the from the filters input and from the input channel. Okay, so that's why we need to apply some sort of zero padding on the boundaries of zero, on the boundaries of input, and then we can perform element wise multiplication successfully. That's why there is a necessity of this zero padding. This is the generic architecture of CNN. See here. Here, see you, this input is there. On this input we are applying this filter. Okay, this is my first filter, this is my second filter. Okay, and then it is generating this first feature map and then second feature map. These feature maps are cascaded in the depth-wise fashion or in the z direction. So this is the result of applying first filter on this input. This is the result of applying second filter on the same input. Okay, then finally some more filters are there, then some more outputs, generic feature maps are generated. Finally, this is nothing but the flattened layer. Every entire volume is getting converted into a vector. The entire process is known as feature extraction. See, this time feature extraction is taking place automatically. See, we are not telling important, that feature is not important. Okay, CNN is responsible for automatic feature extraction. It automatically extract the important and dominating features and just ignore the non-important features. After extracting all the important features, then some fully connected layers are there, as we are having these layers in the previous two notebooks, and then finally the classification layer. Initial layers are responsible for capturing the low level features. Later layers are responsible for capturing the high level features. Uh, CNN is generally associated with one more layer. The name of that layer is max pooling layer. See, suppose this is the feature map generated, like the result of applying filter on the input. So we generated this. So now max pooling is taken care. So if we apply 2 cross 2 max pool, so 2 cross 2 max pool means 2 cross 2 region is considered, maximum is taken out. So 256 is taken out and the remaining all entries are ignored. Then stride 2, next 2 cross 2 region of consideration is this 153, 67, 88 and 43. 153 is maximum, so it is taken out and like this. It is nothing but extracting the dominating or important feature. It is nothing but extracting the dominating and important feature. This is the second most important layer of CNN. Then another layer is there, that is nothing but dropout. Basically, it preserve the regularization technique. It preserve that it prevent overfitting problem. So various other methods are also there like L1, L2 regularization, but here we are using dropout regularization. You can understand dropout like this. If it is written dropout rate is equal to zero point 0.2, means 20% of the all the neurons are just shut down. We will not consider those neurons in the forward and backward pass. Those parameters are not getting updated. Those neurons are not taking part in the learning process. If rate is equal to 0 means all the neurons are working. If rate is equal to zero point 0.4 means 40% of the neurons are not working. This is the entire architecture. Input is there, then convolutional layer. Convolutional layer is generally followed by max pooling layer. Convolutional, then once again dropout, then max pool, convolutional, max pool, dense. Some more fully connected layers are there, and finally the output layer. So this is the generic architecture of a CNN layer. So far we have studied this MNIST and ASL data. Now we will see the third notebook, that is ASL CNN. Just click on the third cell, ASL CNN. See, what is the difference between first, second and third notebook? In first notebook, we created a model. Which model? Deep neural network or plain dense neural network. For which data set? For MNIST data set. Fine. In the second notebook, we created once again dense neural network. For which data set? For American Sign Language data set. Now in third notebook, we are creating Convolutional neural network for which dataset? For once again American Sign Language dataset. See, if you compare the first and second notebook, the neural network is same. Okay, datasets are different. Here MNIST data, here ASL data. If you compare three, dataset is same, American Sign Language dataset, but the networks are different. In second we are using deep neural network, in third we are using convolutional neural network. Okay, now we will start the third notebook. These are the simple library importing. Okay, just run this cell, press shift enter. Now once again the same data set is there, so we are very much familiar with the data set. American Sign Language data set, train DF and validation DF. Then popping these labels, shape is this. See, previously the data was in the form of vector, but now we are interested in applying two-dimensional filter. Now we are interested when we are interested in applying two-dimensional filter on the data. So data should also be two-dimensional data. So now this time that vector 784 sized, this should be first converted to 28 by 28. So here see, we are doing performing this reshape operation. So image height is 28, width is also 28, channel is equal to 1. So we are performing this reshape. Now see, what is 5 over here? 5 is nothing but the total number of sample, like it is nothing but the batch size. Okay, 1 is nothing but the number of channel, and 28 is nothing but width and height. Now once again in this example there are 4 fix me's. This is first, second, third. Okay, we need to do the reshape. Once the data set should be initialized, what should be the shape of the data, that we need to figure it out. Okay, what we are doing over here, once the data set is initialized, training data and validation data, first of all we are removing the label xdf.pop. Okay, we are removing this label. Then we are normalizing it, we are performing this reshape. We are device is ready or not, and if it is ready then we are sending the data to the device. Get item is extracting the image and the label, and length is returning the length of the item. Okay, so we need to fix me. We need to do all this. Fix me should be first cleared, or otherwise we can see the solution over here. See, this is the solution. First, this was my first fix me. So we need to pop the labels. Then this is the first argument, second argument, image size. Sorry, image channels. How many channels are there? Then image width and image height. Just run this cell. Now next thing we need to create the data loader. See, batch size, my data set. First of all, this my data set is initialized. What we are passing? We are passing train df. Just look at this. When we pass this train df, then labels are removed. Labels are assigned to training set images, training set labels. Then remaining part is assigned to training set images. Normalization is done and reshape is also done. Now data loader is created. Training data batch size is 32 over here and shuffle is equal to true. Then training length is equal to length of this data set. Similarly, this is validation data for same thing that we are doing for validation. See, shuffle is equal to true. That was not there. We need to do this. This is my batch. No issue. Now see, batch of 0 means images and batch of 1 means corresponding labels. So what is the batch size? 32. And what is the shape of one image? 128, 28. One is why one? Because single channel is there in the image. 28 is the width, 28 is the height. Batch of 1 means corresponding labels. See how many images are there? 32. So how many labels would be there? 32. Fine. Now creating the CNN model. See, number of classes 24. Kernel size or filter size that we are taking at 3 cross 3. At this point of time, just ignore this flatten image size. So it's a sequential model. First convolutional 2D. So image CHS, total number of channels in the image. Then how many filters that we are applying is the second argument. 25 filters we are applying. What is the filter size? 3 cross 3, kernel size that we already defined. Then stride is equal to 1. Then padding. Are we applying any padding over here? So see, padding is equal to 1 over here. So convolutional 2D, after that batch norm 2D, then ReLU, okay, then max pool 2D, 2 cross 2 max pool. So this entire thing is nothing but my first convolutional layer. Okay, broadly this is the convolutional 2D and it is the convolutional layer, but these are the supporting layers of convolutional 2D: batch normalization, ReLU, rectified linear unit, max pool 2D. All these are the supporting layers. You can imagine that with convolutional 2D. So this was first convolution, then second convolutional. See, 25 filters that we are applying in first convolution layer, 50 filters that we are applying in the second convolutional layer. So this is my second convolutional layer. Then third convolutional layer. In third convolutional layer, we are applying 50 filters. Okay. Then batch norm and then ReLU max pool 2D. Now this flattened image size is coming into picture. And what is this flattened image size? Here in linear layer, we need to define the input and output shape. So input shape is 7533. This 7533 is nothing but output of this max pool 2D. See, we already defined over here. Flattened image size 7533 is nothing but the output of this max pool 2D, which act as the input to this linear layer, and after that 512 neurons are there in that. Then 30% dropout that we are applying, then rectified linear unit. Finally, this is once again linear layer where 512 neurons are acting as the input and number of classes, that is 24, will act as the output. See, these are nothing but the explanation of all these things: batch normalization, max pool 2D. We already discussed this. Dropout, then flatten, then linear layer, and finally the summarizing the model. Now summarizing the model, first of all we need to compile, we need to check the device, and we need to send the data to the device. This is the model summary. Next things are exactly same as we did in the previous notebook: cross entropy loss, optimizer, then batch accuracy that we need to define, then train and validation function. See here, this fix me should be written over here. Then this is second function. You can see the solution also here. This is the first one, validate. Then this is my second one. This is train. Just run this for 20 epochs. In previous notebook also we run the say things for 20 epochs. This time also we are running it for 20 epochs. We will try to compare the result of the first and second. Sorry, second and third. Like this American Sign Language with deep plain neural network, and this is also American Sign Language with convolutional neural network. We will try to compare the both of these results. This is my previous results. This one. 97.28 was training accuracy and 80% validation accuracy. These are the epochs. This is the epoch 18, and finally the epoch 19 would be there. For 20 epochs we run. Now we need to compare this. See the improved result. Training accuracy is almost 100%. Training accuracy is almost 100%, and validation accuracy is 97%. Validation accuracy is around 97%. Now, in previous one, when we used deep neural network, training accuracy 97% and validation accuracy 79%. See this difference and just compare this difference. See, difference is there here also, but this difference is very low, but this difference is very less. Okay. The reason is that here we are using CNN model. CNN is very efficient model as compared to deep neural network. The is that it is using with less, it is trained with lesser number of parameters in comparison with deep neural networks. Okay, so this was the CNN. Now just clear the GPU memory. Fine. Next, notebook number 4A and 4B are based on augmentation of the data set. Notebook number 5A and 5B are based on transfer learning. So we start with the augmentation. First of all, we will see this presentation based on augmentation, like what are the various types of augmentation and what is the necessity of it. And then we will move to the notebook. See, these are the fundamentals. Sorry, these are nothing but the augmentation and deployment, fourth notebook. If we perform augmentation, then we introduce the variance in the data so that the generalizational performance of the model could be improved. There are various types of augmentation. This is the first one, flipping. So suppose this is my image. If we perform horizontal flip, just flip the image horizontally by 90 degree. Okay. Then this is vertical flip. Just flip the image vertically. Okay. So these are flipping. Rotation. Image is there. Just rotate it by 45 degree. Rotate it by 90 degree, 135, 180 degree, 225. These are the rotation. Zooming. This is my original image. Zoom it by 10%, 20%, 30%, 40%. Width and height. Original image is this centered image. Now this is width shift. This is height shift. Then homography. Brightness. Change the brightness. Then channel shifting. Okay. Now we will move to the next notebook. What is the difference between third notebook and fourth notebook? Exactly same thing that we are doing, but this time we are augmenting the data set. Same data set is there. See, if we compare third and fourth notebook, so in third notebook, American Sign Language data set is there. In fourth also American Sign Language data set is same. In third, CNN model is there. In fourth also CNN model is also same. The difference is this: in third notebook, we are not using data augmentation. In fourth one, we are using data augmentation. The remaining code would be exactly same, no difference. Now see, this is data augmentation. Just import all these libraries which are required. Then image height, width, channel is equal to 1, number of classes 24. Then train df, validation df defining, and this is class. Then get item length, everything is same that we did in the previous notebook. Number of n is equal to 32. Okay. Then train loader and validation loader, every single cell. Previously all these things was scattered across different or multiple cells. Just run this cell. Next, model creation. This time we are creating the model with the help of this custom data set. So self dot model, this these are the model that we are creating. Convolutional 2D, input channels, output channels, filter size, stride, then followed by batch normalization, ReLU, dropout, and maxpool 2D. These are the supporting layers for this convolutional 2D, followed by forward pass. Like what is the output of this? Now see, flattened image size that we already defined. This is my base model, nn dot sequential. This is my sequential model, my convolutional block. So this is my image channel that we already defined. Then this is my output channels, okay, and 0. See, when we define this my convolutional block, what are the arguments that we need to pass? This is my convolutional block. These three things that we need to pass: input channel, output channel, and dropout. Okay, so just look at this. This is my first creation, first convolutional layer. So these are the number of channels in the input, then 25 output channels, and dropout we are not using over here. Once this is called my convolutional block with these parameters, then which are getting created? These layers, first, second, third, fourth. These 5 layers are created. Okay. When we call when we call the second one, okay, then once again that object is called, once again those 5 layers are created. Then third one is called, once again those 5 layers are created. Okay, these are nothing but the output of applying this convolutional layers. After that, after applying these 3 convolutional layers, we are having flattened layer. Every volume is converted to a vector. Then some linear layer are there. Output of this last convolutional layer is 7533. That's why here this is we defined here. Flattened image size is 75 multiplied by 3 multiplied by 3. Here in this linear layer, output is 512, dropout is 30%, ReLU, and this. Exactly same network that we built in the previous notebook, but the style is different because here we are using custom data set. Model is created. Fine. This time cross entropy loss, then Adam optimizer, and then finally the model is getting printed over here. See, when we call this first one, when we call this first 25 channels in the output, okay, then this is corresponding to these 5 layers: convolutional 2D, then batch norm, then ReLU, dropout, and maxpool 2D. Okay, these layers are responsible for that very first line. Okay, see the sequence: convolutional, batch norm, ReLU, dropout, max. And what is the sequence over here? Convolutional, batch norm, ReLU, dropout, maxpool 2D. Fine. Then second convolutional block. Second convolutional block, once again, same sequence: convolutional, batch norm, ReLU, dropout, max pool 2D. Then third convolutional layer, sequential, convolutional, batch norm, ReLU, dropout, max pool 2D. Fine. Then flatten layer is there, some linear layer, dropout, ReLU, and this is nothing but the entire architecture. Fine. So far, we have not used any augmentation. Now we will introduce the data augmentation over here. Just look at this. This is data augmentation. First of all, we are taking the very first image from the training data. It is passed to this row 0. We will remove the label. We will normalize it. We will reshape it. Okay. We will perform this, convert it into tensor, and then we will print the shape. So this is my x of 0 dot shape. It is nothing but the very first image in the matrix form. Now what we will do, we will try to apply this type of transformations, like this type of augmentations on this matrix, and we will try to figure it out the output. This is my image. What is the shape? Shape is this 2828. Okay. Now we are applying random size crop. Okay. How it is applied? Transform dot compose, transform dot random size crop. After applying random, this is the outcome: width and height. It should not get changed. Scale is equal to 70% random. After applying random crop, 70% of the image should be there. Okay. And ratio is equal to 1 by 1. Ratio is equal to 1 by 1 means width divided by height. That should be same because it is there in original image. Now we will see when we apply this transform on this image. Which image? On this image. So here we can see when we apply this, how the image is printed. See, it's nothing but a random crop. Here we can see image is shifted little bit left. Okay. But the size is not getting changed. It is 28 by 28 only. Okay. You can verify it by printing the shape. Now horizontal flip. Horizontal flip. First of all, we need to compose this transform. Then we need to perform the horizontal flip. Okay. See, when we are printing horizontal flip, then the image is like this. Then random rotation. So random rotation is 10 degree. Now we are performing this random rotation. Just check it out whether it is shifted slightly 10 degree. Here we can shift, we can just increase the degree 50. See here, this degree is increased, but it is not getting clearly visible over here, like how much this image is tilted when we applied this 50 over here. Then color jitter. Color jitter is having this four transform: brightness, contrast, saturation. Okay, this we can use over here. So with this transform, the image can be converted like this. Now finally what you will do, you will compose or you will club all these four transform. Which four transform? Random rotation, random size resizing, cropping, then horizontal flipping, and color jitter into one transform. See, one thing that I want to explain you, we are here applying horizontal flip. We are not applying vertical flip. What could be the reason? Because see, when we apply horizontal flip, then the category would be same. But when we apply vertical flip, then the category of the image might get changed. So this should not happen because it's handwritten digit. Sorry, because it is American Sign Language data set. So vertical flip is not allowed over here. Horizontal flip is allowed. It completely depends on the context of the application. Now, when we apply, Sorry, we have not run this cell. So entire everything is there in this random transform. Everything is there now. Transform. There are multiple combinations of this. When we apply random transform on that image, so this could be the outcome. Now training with augmentation. See, this time the function was there previously, get batch accuracy. This time that function get batch accuracy, that is defined in the utility function. Which utility function? Here you can see one utility dot py is there. So that function is shifted there. Now two things are there: train and validation df. See, exactly same functions are there: loss, accuracy, model train, xy are coming from data loader. But see what we are passing, we are not passing model dot model of x that we passed in the previous one. Just look at this. This was my train. What we are passing previously, sorry, this one. Output is equal to model of x. This time output is equal to model of x that is not used over here. First of all, it is getting through random transform. The images that are loaded, see, this is my train loader. A batch of 32 images are loaded, but after loading, it is first transformed with the help of augmentation and then it is passed to the model. This is the only difference. This is the only difference. And see, this is done in training, not in validation. Transformation or augmentation is applying only at the time of model training. Augmentation is not used at the model validation or in the model testing. It is used for model training only. Exactly same things are there. Just run this cell. Now run this model for 20 epochs. Now we will also see how we can save the model. How we can save the model. This time, see, model is not over here. So first of all, we will see this model deployment. So now the model is trained. We can save the model on the cloud, so that once again in future we require that particular model, so we should not train the model again. Model is already deployed on the cloud. So what do we mean by that model is deployed on the cloud? It means that the architecture is stored on the cloud, as well as the trained weight or the final updated weights. Those are also stored on the cloud. And once again, we reload that particular model from the cloud. Then that model is loaded into the memory with the same architecture and with the updated trained weights, and it is ready to use. Two things are stored: model structure, the architecture, like how many neurons are there in first layer, how many neurons are there in the second layer, what is the first layer, what is the second layer, whether it is batch norm, whether it is ReLU, like this, and what is the final updated trained parameters. So model is trained over here. See, here, see, you can observe the difference is getting reduced. The only difference between this notebook and the previous notebook is that here we have used augmentation. This is the only difference. Exactly same architecture was there in previous notebook. Same architecture is there in this notebook also. Same data set. Only augmentation that we used. So this time it is 99% and it is 98.41%. What is the result in the previous case? In the previous case, validation accuracy was 96.85%. This time validation accuracy is 98.41%. Ultimately, we want that validation accuracy should be as close to the training accuracy. Okay. We introduce augmentation. So model is performing good on the validation data. This is about this is the ultimate aim. Now just save the model. Torch.save base model, and this is the name model dot. Now here we can see uh, model is saved over here in this directory only. Just look at this model.pth. So model.pth is saved over here. Fine. Now we can clear the GPU memory. Now in the next notebook, model is deployed on the cloud. We in the next notebook we will see how we can use the deployed model back. So the next notebook is ASL prediction. This is the next notebook. So this notebook is deploying the model, fine, and using the model. First of all, load the already trained model from the disk. Then reformat image for a model trained on the image on images of different format. Okay, we should be very careful what the model is taking and what it is producing. We should provide the input in that format only or in that shape only. That's why first of all we should check carefully what the input that we are providing to the trained model and what it is generating. Fine. These are the supported libraries. Then next one, loading the model. From utility, import this my convolutional block. This is the utility that is required over here. Now model.pth. Model.pth is once again loaded in the model. We can also print the shape, exactly same shape it's printed. Along with the shape, the parameters are also trained, updated parameters. We need to shift the model to the GPU, preparing the image for the model. See, we are having some images in this data ASL image folder. Just look at this. This is my data. This is my ASL image. So some images are there, a.png and b.png. Okay, we will work out on these two images, a.png and b.png. So first of all, we will write a function for showing the image. See, we will write the function show image, and then we will call this function. Sorry, we are calling this data ASL image. In that b.png, it is passed. That is the image path, and it will show the image. Let's look at this image. What is the shape? Shape is something random, like 180 by 180. But our model do not understand 180 by 180. Moreover, it's a colored input. Our model is taking that 28 by 28, and it's a grayscale input, grayscale image. Okay. Now scaling the image, we need to first scale the image. Then only we will provide this image for the prediction. So first of all, read image. And we will read image. Sorry, we will first of all use this io.image read mode in the gray mode. Okay, and we will call this. So this is the tensor. We will see what is the shape. Shape is this 184. So ultimately, what we did over here in this particular cell, we converted into grayscale input. Okay, that's why this is 184 186. Previously it was 3 184 186. Now this 184 186, that is also not compatible with our model input. So what you will do, we will set scale to true in order to convert this to previous range is 0 to 255. Our model is expecting the input in the range 0 to 1. Resize. Our model is expecting the input in the range 28 by 28 and converting it into grayscale input. Width and height, that is defined, and these are the three compose. First of all, scale is equal to true. Convert range 255 into 0 to 1, then resize width and height and transform into gray. After that, apply these things on which image? On this image. Okay. Then just print this pre-processed image. So this is my pre-processed image. This time it is 28 by 28 shape that we can print 128 28. Now our model can accept it. Now our model can accept this input. We can also print this. So this is my image. Now making prediction. Our model is expecting this images in the form of batches, but this is only single image, so we cannot provide this as it is. First of all, we need to add one more dimension at the 0th index. Okay, see, previous shape is this 128 28. Now the new shape is 1128 28. So this 128 28 is nothing but shape of one image, and this one indicate the number of batches. Okay, sorry, no, not number of samples. Okay, in the batch. So here only one sample in the batch, and this is my sample size. With the help of this unsqueeze, we can add one more dimension. With the help of squeeze, we can remove the dimension. We can also mention over here at what index we can add the dimension. Okay, now this time, first of all, we will move it to GPU, and then we will see the output. So batched image GPU, this is my final batch, and we can perform the prediction over here. Now this is my result. So total, how many categories are there? Output categories in ASL model, total 24 categories. But see, this is not readable prediction. How can we read this prediction? This is the output of first neuron, this is the output of second neuron, this is the output of third neuron. Okay, so we will try to convert this into some readable prediction. So we will use this orgmax. Now we will see the prediction. Here what we are doing, we are index of the largest entry on this vector. So the largest entry is this 13.59, and the index of this is 1. So it is predicting 1. But it is also not meaningful prediction, because we need to predict whether it is A, B, C, D, E, F. Okay. Total how many categories are there? 24 such categories. J and Z are not there. Okay. So we can make it more meaningful. So alphabet dot prediction is nothing but alphabet of 1. Alphabet of 1 is nothing but this B. So B is printed out. Now we can combine everything into one single variable, into one single function. Okay, there are several fix me, or otherwise you can see the solution over here. So this is my predict later function. Here we need to pass the file path. So this is my file path. First of all, show image. Okay, then convert it into the readable mode, then pre-process image. Okay, then unsqueeze 0, add one more dimension, pass it to the GPU, calculate the output, then make it meaningful prediction, and finally it is predicting the later. Just see. After that, we can pass both of this like a.png and b.png. Just call this function predict later. So we are calling this function predict later. Firstly, we are passing a.png, and second time we are first we are passing b.png, and second time we are passing a.png. This was my original image, colored image. This letter is printed out B. Then next, A is the outcome. This is my image. Actually, this is the original image. It is not a processed image. Summary is that you need to see what is our trained model. what it is expecting as input, whether it is expecting input in normalized form, whether it is expecting input in uh, how many channels, in how many channels it is predicting as in the input, whether it is predicting the colored input, whether it is predicting the grayscale input, uh, how it is generating the output, how the output can be converted to a readable format. Everything should be taken care of. So model is there, we need to finalize or we need to fine tune the entire pipeline. This is what all about for the with this fourth and fifth, sorry, fourth one, augmentation. I hope everything is clear over here. We need to clear the GPU memory.
Sir, you are on mute. Sir, it's still not audible.
Is it audible?
Yes, sir, it is audible now.
Okay, fine. Yeah. So is the screen visible?
Yes.
Okay. So good afternoon once again. Let's start with the remaining presentations and the notebooks. So here basically we will see how we can use the pre-trained models, and then we will once again jump to the notebooks. So basically, so far we have seen how we can create the deep neural networks, how we can create the convolutional neural networks, how we can augment the data set, and now we will move to the pre-trained models and transfer learnings. See, the next problem is based on detection of the dogs. So we will try to build an application, automated doggy door, in the next notebook, and the identification of the special kind of dog in the next notebook. Yeah, that is nothing but that presidential doggy door problems. So basically, suppose one problem is there, we can easily recognize, okay, this is a dog image. So probably we can fine tune the model to easily specific types of dog. This is the ideology or philosophy behind this. Like we are having a model which can classify the dog. This is dog and this is not a dog. Okay, so we can fine tune the model, and we can fine tune the parameters of the model so that it can identify or it can detect a specific types of dogs. That is nothing but the transfer learning. So generally what we will do, model is already there. So you can see here the entire structure is there. So we can cut the model from at any particular point of at any particular place. So this is nothing but the remaining part, and this is nothing but another part. Okay, so what you will do, this part will be same, and after that we will add some more customized layer after this, and then we will fine tune this entire architecture. So there are basically two types of transfer learning. One is feature extraction and another one is fine tuning. So in feature extraction, what we generally do, basically we keep the entire architecture as frozen. So we will not update the parameters of the pre-trained model, and we will just use those pre-trained model for extracting or for generating the feature maps. This is feature extraction. Second one is fine tuning. In fine tuning, what we generally do, we just keep one or two layer as as freeze as frozen, and the rest of the, some of the layers are kept as not freezed. Okay, and then we will fine tune the parameters of these layers when once we train the model. This is known as fine tuning, and this happens incrementally. Suppose if we take this slide, and suppose this is the entire architecture which is frozen. We added some architecture over here, we train the model. Now what you will do, you will unfreeze this layer, and then you once again train the model. Then you unfreeze this next layer, and then you once again train the model. This is known as fine tuning. Fine tuning is very efficient as compared to transfer learning, because fine tuning captures the generics of the data set on which the pre-trained model was already trained, as well as on the new data set which is available. Basically, transfer learning is used when we are having a data set which is very small in size. So basically what you will do, one pre-trained or one large network is there which is already trained on a huge corpus. So we will just use this particular trained architecture to fine tune this on our smaller size data set. If we do not apply this transfer learning and we perform the model training from scratch, then it will perform very good on the training data, but it will not able to generalize the data which it has not seen before. This is the overfitting problem. That's why we go for transfer learning concept. Now we will see how we can use the pre-trained models. So we used convolutional neural network before this. So basically, pre-trained CNN models. So there are various kinds of pre-trained CNN models. So some examples are VGG 16, VGG 19. Basically, this 16 and 19 represent the number of layers in those CNN architecture. Then LXNet is there, InceptionNet, GoogleNet. These are also pre-trained CNN. So here in our experimentation, we will be using VGG. So basically, these are the objectives. We will use torch vision to load a very well trained pre-trained model, then process our new image to work with the pre-trained model, then use this pre-trained model to perform accurate inferences on our own images. So these are the objectives. Basically, we will just import these libraries. The problem is known as automated doggy door problem. First of all, we will load the model. So by loading the model, we are importing the model architecture, as well as we are importing the model weights. As I have already, told earlier, that model is nothing but the architecture plus weights. So VGG 16 was already trained on a huge corpus. Okay. So here we are importing the architecture of VGG 16 in the first line, and in the second line we are importing the trained weights, and we are extracting this VGG 16 weights dot default, and these are stored in weight, and we are store 16 weights into this particular model. So ultimately now we are having this model in which we are having the model architecture as well as trained weights. This model is getting downloaded. Our next task is to transfer everything on the device. Okay, so this is the architecture. Sequential model is there. First layer is convolutional 2D with 64 filters. Filter size is 3 cross 3, stride is 1, padding is 1 cross 1, then rectified linear unit. This is the second convolutional layer with 64 filters. Then this is the third convolutional layer with 64 128 filters. Likewise, this is the entire architecture of VGG16. Now see the input dimension. So here we will see weights dot transform. We will use this function and we will store this weight dot transform in this variable pre-trans. This will allow us to transform the weights as per our necessity or as per the need. These are the transformations available. Crop size 224, resize size 256. These are the mean, standard deviation, and interpolation, bilinear interpolation that we are using. Do not go in the details of this. There are various types of interpolation. So here we are using bi. The thing is that it is equivalent to we are just defining this image width and height as 224 224. This is the standard size that the model is taking. Actual size was this 256 256, but it's a random crop, and after cropping the size is 224 224. And we also ensure that after doing this transformation we normalize this to get this particular mean and to get this particular standard deviation. Now output dimension. So previously this model was trained for the classification of one of the 1000 categories. Okay, now this time suppose our model shape is somewhat different, like we are having some other architecture, model is taking some other output. So we need to first align the expected output and the actual output. So we will just see how we can do this. First of all, we need to write this function. It is just a simple image function which is just showing the image. Here we can call this method show image. So here we can see these are some of the data in which this doggy door images are there. Okay, so 3 images are there. Just call this method. Okay, so this is my image. Fine. What is the dimension? Dimension is something some 1200 to 1800. This is the dimension of this image. Okay, now once again we need to see what our model is expecting as input and what it is generating as output, and how we can get the meaningful prediction. Next we need to pre-process this. What do we mean by pre-processing? See, the model is expecting colored input and a batch of input for processing and to produce the output. So this could be the shape. The very first argument is nothing but the batch number of sample in the batch, and second one is nothing but the number of channels. So it's a colored input. 224 is the width and 224 is the height. We need to process this particular images and we will transform the size into this. Okay, so this is what we are writing load and process images. Here we are passing the file path. First of all, we are printing this original image, then we are taking this file path and we are opening this in a read mode. Okay, and then we perform this pre-trans of this image. It is nothing but the weight transformation. See, we will see what we did in pre-trans. So this was my pre-trans. Okay, weight dot transform, and what we are doing this particular transformation of that original input. Once again, we are adding one more dimension with the help of unsqueeze, because model is expecting a batch. It is not expecting a single input. Okay, that's why we are writing image dot unsqueeze, and at what index? 0th index. So this is the transformation. Now once again we call this function load and process image. So this is my processed image. Previous dimension was this 1200, 1800, 3. After processing this, the size is 1, 3, 2, 224, 224. Okay. It is a batch. Only one sample is there in batch, and this 324, 24 is nothing but the dimension of one sample. Now we can also see how the image is looking. This is my image. Size is 224, 224. Fine. It's a colored input. Only one image is there. Now make a prediction. See, first of all, we will load it. Then we will see the very first index of it. Now, once again, we will convert it into the readable prediction. So here in readable prediction, we will write a complete function which uses all the previous function. So our first function was this show. Second function was load and process image. Then third one is the output of this. Then next one is getting this top k outcome. And lastly, these are nothing but the top results are stored in this particular string, and this string is processed, and finally it is returning the prediction. Now see, when we are passing this, calling this function readable prediction, what is the outcome? So this is my actual shape. Then these are the top results. This is first category, then second, and then third one. Next is this. This was the actual image size. Then these are the top three predictions, and then last is this. So this is a cat. Fine. Now, just imagine that suppose we are interested in doing a class in constructing a classification, or in constructing recognizes dogs. Okay. So in the original data set, the dogs are categorized 151 to 268, and cats are categorized from 281 to 285 in the original data set on which VGG 16 was trained previously. Okay. So see how we can do this. We will write one doggy door function over here. First we will write show image, then load and process image, and finally it is stored in this. Now we will see extract the maximum one. Here dimension is equal to fix me. We need to look into that what should be there in place of fix me. Then we will see the predicted index. If the predicted index is in the range from 151 to 268, so from this 151 to 268, then it is considered as dogs. If it is in the range from 281 to 285, then it's a cats. Otherwise, you are not a dog, stay outside. This message should be printed out. What should be there in place of fix me, that you can see over here from this solution. I think dimension is equal to 1 should be there. Okay, this is fine. So this is my, now see, first two images are for dogs. So here the output, this is doggy, come on in. No, this because the predicted index is 294. So this message is get displayed. You are not a dog. Then next one is for this dog, and then last one is for cat. Fine. So this is the model which is differentiating dog versus cat. Okay. Actually, this model is not differentiating dog versus cat. It is predicting everything. We are just taking the output of those models and we are comparing it with the actual index. Okay. Now we will see how transfer learning is implemented in the next notebook. Now see the transfer learning concept. First of all, we will prepare a pre-trained model for transfer learning. We will do the transfer learning with our own small data set. Then we will fine tune the model. So these are the three things that we will do. First of all, we will prepare a pre-trained model. Then we will perform the transfer learning and we will fine tune it. First of all, we will download the pre-trained model. Here, see, once again, the same thing that we are doing as we did in the previous notebook. It is transferred to device. Then freezing the base model. See, VGG structure is frozen now. And how we can do this? This is the very simple line. You just try to understand this. VGG model dot require gradient is equal to false. Okay. If we pass false in this required gradient, it means that we cannot update the parameters of the model. It indicates that VGG 16 is frozen now. Okay. If we pass true here, it indicates that the parameters of this VGG 16 can be updated. That we will do when we will do the fine tuning. But at this point of time, we are just keeping this particular parameters unchanged. So here we are passing false. Now all the parameters are frozen. This was the title of this, freezing the base model. The base model was VGG 16. We are freezing this model. Now we are adding another layer. So how we can add the one more layer over this? See, this is my number of classes. Number of classes is equal to 1. Model is this sequential model. The first thing is in the model is VGG model. That entire model of VGG 16. Okay, VGG 16 was a classifier which classify into categories. Okay, so we are adding one more layer. Input will be those 1000 neurons and output will be 1. Out in final output layer, only single neuron will be there. Fine. And once again, we are transferring this onto the device. So VGG 16 structure was there. On top of that, we are adding one more layer. In the last layer, only single neuron is there. Now we will do the transfer learning. We can also see like which are the layers which are frozen, which are the layers which can be updated. So if we write or if we extract every layer like my model dot parameters, okay. So here we can print. You can see over here all the layers are frozen. We cannot update any particular layer except the last two layer. Last layer was unfrozen and we added another layer in which one neuron was there. So except these two layers, every other layer cannot update its particular weights. Now we want that model should update its weight. Now we will write this VGG model dot require gradient. When we pass true, it means that VGG 16 is now unfrozen. If VGG 16 is unfrozen, then we can print once again the same, which layer is frozen, which layer is not. Okay, just see the outcome. Here you can see every layer is unfreeze. It means that we can update the parameters of each of these layers, but actually we do not want this. Once again we will make this frozen. We need to work upon this my model. Fine, my model, there are two things, one is VGG, another one is the last layer. Now see how we can do this. Now next one is compiling the model. So here see, because only one thing is that in the last layer, so because if only single neuron is there, then we can use this binary cross entropy loss. So if it is a class A or class B, that's what we are interested in doing. So we will just use binary cross entropy loss over here. This is the loss function, binary cross entropy BCE, with this logit loss, Adams optimizer that we are using, and then we will transfer it to the device. Next, data augmentation. We will call this transform. Okay, these are the data labels. So we are once again creating our custom data set. So two labels are there, bow and not bow. So this is my initialization definition. Next, we will see the data loader. So train loader as well as validation loader that we will see. Where data is there, data is very small and data is available here in this folder. In data, presidential doggy door. See, in this particular folder, there are very small data set is there, presidential doggy door. So two folders are there. This is training images and this is validation images. Fine. So we have created this train loader as well as validation loader. Now we will do the augmentation. So these type of transformation that we are applying: random rotation, random resize crop, horizontal flip, and color jitter. Image width and image size, height is this 224, 224. Just run this. Next one is this training loop. See, previously we are using get batch accuracy function, but this time we are using binary cross entropy loss. So we could run the output through the sigmoid function. The sigmoid function is used for binary classification loss function. The formula is 1 upon 1 plus exponent of minus x, where we can write sigmoid of x is equal to this. And greater than 0, then we can consider this as a close to 1. And if it is less than 0, then we can consider this as a another class. So this is my, once again, we are redefining this function get batch accuracy. Now we will write train and validation function. So here we can see check grade is equal to false. Okay. In training, we are writing check grade is equal to false. So we will see the meaning of this. It's a training method. So loss is equal to 0, accuracy is equal to 0. We are initiating the training, model training. Then we are taking it the data, or we are loading the batches from train loader. First of all, we are doing squeeze, okay, and then see here, we are passing the augmented input. Random trans is nothing but the result of performing augmentation, and then we are passing it to the model, okay. Then it's nothing but optimizer initialization, then finally this loss function, then gradient calculation and parameter update. So here we need to check. If check gradient is equal to true, then we will see it is a last gradient, and if check gradient is equal to false, then we simply come over here and we will print the final loss and final accuracy. Just run this cell. Now this is the validation. Here we are just calculating the output. No gradient updates are there because we are writing torch.no grade over here. Okay, finally then this we are running it for 10 epochs. See here we are running this my model. My model is nothing but a combination of VGG 16 plus the last layer that we have added. So this is nothing but train and validation. So far we have not done the fine tuning because the VGG 16 was frozen. Okay, and we will just compare the accuracy. Okay, for 10 epochs we train the model. So this is my accuracy, 90 and 96% training and validation respectively. Now we will see how we can fine tune the model. See, when we write VGG 16 dot require grade is equal to true, it means that the parameters of those layers of VGG 16 can also be updated. Okay, so we are unfreezing the base model. Now once again, for 2 epochs we will train the model. So this is what this is how we can implement the transfer learning. It's very simple. You can unfreeze layer by layer also. Like it is also possible you can unfreeze some of the layer, you can freeze some of the layers, and then finally you can fine tune or you can retrain the model once again. Now we can examine the predictions. This is the function for writing the image, for just printing the image, and this is the function for final make prediction. Here we just need to pass the file path. First of all, it is printing the image. It is just and then finally the image is open. Then we apply this transformation and sending it to the device. Then we are adding one more dimension to represent this as a batch. Then we are making this prediction, and finally these are the prediction that we are returning over here. Fine. So if it is negative, then, and this is positive. Like, so negative number the bow, and positive number predicting that it is something else, and negative number specifically indicating that these are nothing but the presidential doggy door. Now we can write the definition for presidential doggy door. Here we just need to pass the image path. It will make the prediction, and here if fix me, then it should print this, otherwise not. So what should be there in place of fix me, that you can figure it out, or you can just look at the solution. If prediction is less than 0, then it's a bow, otherwise it is something else. So we can once again run the same to self. It's not a bow, and this one, it's a bow. Now you can just shut down the kernel. So I can just summarize the things that we did in this particular notebook number 5A and 5B. So this was nothing but the transfer learning. Basically, every time we are not interested in training the model from the scratch. So model is there. Pre-trained models are already there, which are trained on the large annotated data set. The main problem is the data labeling. So if the labeled data set is already there and the large model has already trained on the large data set, then there should not be any necessity to retrain every time from scratch. And even though when we are having some smaller amount of labeled data, then we should not train the model from the scratch, otherwise it will overfit. Then we should go for transfer learning concept of things. We can just use the pre-trained models that is similar to our application, and then we can fine tune it on our data set. So two types of fine tunings was there. One is feature extraction, in which the base model was entirely frozen. We will not update any parameter of the base model. Second option is fine tuning. We will incrementally unfreeze the layers of the base model, and we will perform the retraining of the model. That is nothing but fine tuning. So fine tuning perform better as compared to feature extraction. So these are the things.